We're back. Let's talk about how to predict the products of oxidations with potassium permanganate and ozone. And I'm going to show you a quick little way to approach this type of problem that will make an otherwise semi-complicated topic into something a little bit more manageable. One thing I would like to point out, however, is that you're still on the hook for knowing the mechanism of ozonolysis, so don't forget about that. We talked about that in the previous video. Alright, so here's the deal. You will be presented with a molecule like the one that we have right here, and the idea is that because we're treating this with potassium permanganate under basic conditions and heat, we are expecting to break apart the double bonds and the triple bonds, and we're going to be replacing them with a few things. Now, the way I personally do this type of problem is that I copy and paste pretty much the reactant that I'm going to be playing with, and here I'm going to place the table that tells you what you expect to get if the alkene carbon has one H, if it has no H's, if it has two H's. So in other words, 0 H's, ketone, 1 H, carboxylic acid, 2 H's, carbon dioxide. And so we're going to kind of analyze what we're dealing with here to make sense of it. But instead of really dealing with the table here, we're just going to let the structure tell us what happens. And so what I do is I say, okay, look at the alkenes, those three alkenes are going to be removed. But I'm going to first artificially elongate those alkene bonds. And the reason why is because I want to make up a little bit of room for what I'm about to substitute the alkene with in terms of functional groups. So once I elongate the alkenes, exaggerate them in other words, I'm going to erase them altogether. I get rid of them. And then the carbons that used to be part of the alkene, so this carbon over there, this carbon over here, that carbon, that carbon, that carbon, and that carbon, all I'm going to do is add a new double bond to oxygen. And so what now we're doing is creating three fragments, and of course the oxygens are not bound to each other, so these are three distinct fragments as of now. Okay, now the last thing is that once that you have added the carbonyls to all the corresponding carbons where the alkenes used to be, you're gonna look for carbonyls that do have hydrogen bound to them. In this case, we have three of those that have hydrogen. All you really have to do, as long as you're performing this with potassium permanganate under heat, is replace those hydrogens with hydroxides. That's all you have to do. And as you can see, actually the process is not as bad as you might have thought before. For sure, the mechanism that I was showing you, it's very involved, but I kind of wanted you to see what the potassium permanganate is actually doing for you to make sense of these reactions, because there's nothing more annoying in chemistry than to be told this is what happens without being told why it happens. And if you are still curious about how these type of reactions happen, I recommend you watch the video prior to this one on the lecture series just to make sense of it. But as far as predicting the products, that's all you have to do for the alkenes. Now, mind you, this molecule still has alkynes present, so we're going to take care of that next. And to remind you, the alkyne carbon, if it has no hydrogens bound to it, we're expecting a carboxylic acid. If it does have one hydrogen bound to it, we expect carbon dioxide to come out from that particular point. And so for the alkynes, we're going to break those bonds, and pretty much what that means is that we're going to erase them. So if we erase them, don't forget that here you have a terminal alkyne, or used to have a terminal alkyne, which means that you will have a carbon with one H kind of lingering up there, but you gotta remember to put it there. The carbon is not disappearing, we're only erasing the bonds. All right, now what happens is that for every one of these carbons, right? So this carbon that was internal, this carbon that was internal, this carbon that was also internal in the alkyne series, all we're going to do is replace them with carboxylic acid. So we have carboxylic acid at this end, which is this, carboxylic acid right here, which is the carbon over there, and then we have carboxylic acid over here, as you can see on the diagram. And then that brings us to the lingering CH that's left by itself. Well, that is a carbon bound to one hydrogen, so we are going to turn it into carbon dioxide. And the moment you do that, you have arrived at all 1, 2, 3, 4, 5 products that you expect to obtain from the ozonolysis of, the potassium permanganate oxidation of this alkyne molecule. Okay, now ozonolysis is very similar. In fact, it's even simpler than the potassium permanganate case because the steps are identical, but we're going to meet some of the ones that we have used for potassium permanganate. So we copy the molecule, we exaggerate the alkene bonds, so let me exaggerate them, and then we're going to erase them. Let's erase those double bonds. And like before, we are going to add a carbonyl double bond oxygen to each one of the carbons of where there used to be an alkene. So we're going to have carbonyl over here, carbonyl over there, carbonyl over here, 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 and here. All right, so let's do that. Now the beauty of the ozonolysis problem is that once you do this thing for the alkenes, you're done. There's nothing else to be done for the alkenes. So you don't look for the H's. If the carbonyl has an H bound to it, it will keep that H. And the reason being is that unlike potassium permanganate, ozonolysis doesn't have hydroxide present. The conditions are a lot, well, in some ways you could say milder. Definitely you don't have a base around, so the removal of protons is not going to happen. And also you don't have a really strong metal Lewis acid present, so that makes it difficult to remove the aldehyde hydrogen. All right, now that brings us to the alkynes. And right here, what you gotta remember is that if the alkyne has no hydrogens bound to it, that carbon will be turned into carboxylic acid. But if you do have one hydrogen bound to it, it will generate formic acid. So let's start with the alkyne down here. Okay, so let's label it red. That carbon doesn't have hydrogen bound to it. This carbon doesn't have hydrogen bound to it. So we'll turn them into carboxylic acids. Now for this other alkyne, let's turn it pink. The carbon right here is now bound to hydrogen. So we will turn this carbon over there into carboxylic acid as well. Now the last carbon, the carbon right here, does have a hydrogen bound to it. So that carbon, if you want to look at it this way, you want to keep the hydrogen, but you will still turn it into carboxylic acid. So in essence, everything alkyne related is turned into carboxylic acid. Whether you have carbon or hydrogen bound to it is pretty much irrelevant. You will turn it into carboxylic acid. Now the one right here, where hydrogen is bound to the carboxylic acid functional group, is known as formic acid. So that's the identity of this molecule right here. And you still have 5 fragments, but they are different just a little bit. The ones that dealt with the alkenes, only the middle one and the one here on the right side are different. But then the product right here on the very top is definitely different from the first one. So this is just a little shortcut as to how you can do these problems. So highly recommend that you draw the molecules, exaggerate the length of those bonds, erase them, and then replace them with carbonyls. And if you're doing ozonolysis, all you have to do is remember that you just change the alkyne carbons to carboxylic acids. If you're doing potassium permanganate, don't forget to change the hydrogens of the carbonyls into hydroxyls, in essence turning them into carboxylic acids. Okay, so hopefully you found this helpful, and with that being said, I will see you on the next video. Bye bye.